Hello again, everyone. All right, so um, this is a little bit different lesson today. It's not really it's not like a lesson from the course. I just wanted to go over the lab. So hopefully you've already found the lab on the website. Um, it's going to be a little bit different than the sheet. So I wanted to go over my expectations for what a lab looks like. This will be a formal lab, and also sort of what things you need to do for this lab and how it works, because it's going to be a little bit different. We're not in a lab. It's going to be done using a simulation. So I just want to take some time and go over things. So you hopefully have found the lab sheets. I'm just going to switch over to Chrome here. So this is our website, right? This is lesson unit 1, and at the bottom this is the lab. So if you click on the lab sheet, it'll bring up our lab sheet. And now I couldn't find a way to get rid of this part of the investigation. So we're only doing 3.3.2. Okay, so we're doing this. We're analyzing uniform motion. We're going to try to see if we can derive the formula for centripetal force with respect to frequency, okay, and mass and radius. So we're going to try to see if we can find the relationship between all those things using a spinning mass on a string. Okay, so there's a lot here and some different numbers and stuff, but we're going to have to change everything. Okay, and I'm going to go over what I mean. Um, so this lab sheet isn't actually particularly useful for us. So let's instead go to the simulation. So the simulation looks like this. Okay, and you click on begin, and it'll bring you to our simulation. And we have 3 variables that we can control in this lab. Okay, so we can control the mass that we're spinning around with these up and down buttons. So right now it's at 25, and I can go all the way up to 250. So there's a whole bunch of different masses that we can choose. You're only going to be responsible for 3. Okay, so we can change the masses. We can also change the length of the string. This is a little bit tricky. There's a little piece of masking tape here that I do this lab, in real life, and you need this little piece of tape stuck to your string to ensure that the string isn't going up and down. We want an equilibrium situation when everything's spinning, and I'll explain what I mean by that. But when you click on this tape, it's going to change our radial size, and you can measure it using this meter stick. Now notice the meter stick doesn't have that many divisions, so your measurement is going to be quite small. Sorry, so your uncertainty on your measurement is going to be quite large. Okay, so keep that in mind. That's an error for the lab. This meter stick is not very precise. Excuse me. So therefore, it's going to have quite a lot of error. And the third thing we can change is the number of washers. The amount of tension that I'm putting on the string is going to be equal to the weight that I'm attached to the string. So I can go 5 washers, and each washer weighs 10 grams. There was a little box that said so, but each washer weighs 10 grams. So right now I have 31 washers, so I have 310 grams or 0.31 kilograms. Right? Make sure everything's in kilograms and meters for our calculations. And yeah, so everything should be in kilograms. So kilograms for washers, kilograms for the moving mass, and excuse me, meters for the length. Otherwise, there's going to be you're going to be off by various orders of magnitude. And when I hit start, everything starts spinning, and it's going to show me the time. Okay, you can watch this thing spin around, and you can play around with it. You can see how fast that's going. And if I hit reset, let's say I have a big mass here, very short string, oh, and very small mass. It's going to spin very, very fast. So this setup isn't very good because it's very difficult to count the number, right? So the way that we're going to do this is to determine the frequency here. Let's reset this. Let's go to a more reasonable size. Okay. So what you're going to do is you're going to count 20 revolutions. You're going to count the period for 20 cycles of our rotation. And you can count that however you want. Wherever your reference point is, you can start over here. So 1, 2, or you can do it at the front here. So 1, 2. You're going to count 20 and record your time. And pause it when you're done. See, you're going to have a little bit of error there as well, okay? Because where you're clicking, it wasn't exactly there. So there's going to be some human error. Well, sorry, it's not human error. Some systematic error caused by human reaction time. It's not a human error. Human errors are mistakes. Those are not systematic errors for our lab. Okay? So how are we going to analyze this? We have 3 variables, right? There's the, sorry, one second, reset. There's the length of the string, so R. There's the mass spinning, and then there's the force that I'm pulling down with. So I have 3 different variables, and I want to see the relationship with them, sorry. So what I'm going to have to do is do 3 different experiments. Right? In science, we can't manipulate 3 different variables. Right? We have to manipulate 2 variables to look for the relationship between those 2 variables while keeping the third constant. So that means there's going to be 3 different things that we're going to do in the lab. Where's my lab? Where is it? That's it here. Okay. So gone over that. Let's just think quickly about what's happening involved in the forces here. Also notice the way that I've labeled this. If you label things, if you make a diagram, if you take a diagram like this and you put it in your lab, please ensure that the title for any picture, including a graph, so graphs have to have titles as well, put it underneath and say figure 1, figure 2. If you really want to be fancy, you can put figure in italics, sorry, and tell me what the name of the thing is. So this is an example here of how things should be labeled for the lab. Okay, so what's happening in this thing? So there's going to be a ball spinning around, right? So for it to spin around, it has to have a centripetal force, right? So let's label some things first. Okay, so first of all, we know that the radius, the distance that the ball is away from the central little sleeve here. So again, notice quickly, I didn't say this in the description here, but there's this sleeve that the string can go up and down in, and it can slide in here relatively friction-free. Okay, there will be some friction here at the corner, but we're going to disregard it. So I have to balance these forces on here. So quickly, M1 is the hanging mass, and M2 is the spinning mass. So keep that in mind when we're looking at the rest of these things. M1 is hanging, M2 is spinning. Okay, M1 hanging, M2 spinning. So again, there is a centripetal force that's making it go around in a circle. Right? Because the ball is traveling in this circle, there has to be an acceleration inwards, v squared over r, of that acceleration to make this go around, and it has to be some force. Now, because of inertia, because of Newton's first law, it actually wants to keep going. So there's going to be a pseudo force. Because this is an inertial force, there's going to be a centrifugal force pulling it outwards, generating a tension in the string. If there was no hanging mass and I tried this, the ball would just fly out, right? So we have to balance it with a force pulling downwards. So the gravity pulling down on M1 is going to balance this inertial force of this ball wanting to continue going in a straight line. That's also equal to the centripetal force. Okay, so all 3 of these force vectors are all the same length. Okay, they're all the same size. So we can say that the tension force, however I measure, whatever, however number of washers multiplied by 10, because each not 10, 0.01 multiplied by 9.81 newtons per kilogram will tell me the force, the centripetal force that's acting on this ball. That's the whole point of the lab. We're balancing, we're putting this thing into a state of equilibrium, sort of. An equilibrium in terms of the string. We don't want the string to go up and down. That's what that piece of tape was there for. The only force we want acting on this is the centripetal force pulling inwards. But again, since it's an inertial force, there will be a pseudo force, a centrifugal force acting outwards that will generate tension in the string, and we have to balance it with gravity. on this M1 down here. Okay, so again, our three variables are M2, the spinning mass, the radius, and M1, how much mass we're putting down here. So really our variable is the centripetal force. So we're looking at the relationship between centripetal force, radius, and mass. Those are our three things. So what you're going to have to come up with is three different tables. And they're going to look something like this. Since this is our first lab, I'm going to give you the tables pretty much. So we're going to do it 3 times for each lab, each section here. So if we're looking at what the relationship between the centripetal force and the frequency as it spins around, we're going to change we're going to change M1. So that's going to be what you're putting in, the amount of tension that we're putting in the string. So we're going to manipulate M1. That's the number of washers, which will tell us the tension in the string, which will tell us the centripetal force on the ball. Okay, so you're going to pick 3 of these. And that'll be your choice, whichever one you want however you want to decide. If you want to have 16 washers, 27 washers, and 5 washers, whatever that is, you're going to calculate the mass of that, then multiply that by 9.81 newtons per meter to give you the force. And remember, that tension force on the string caused by that mass is going to be the same as the centripetal force that's acting on the spinning ball. Okay, so that's going to be my FC. Then you're going to count 20 revolutions and record the time. Then divide that by 20 to get the actual period. And then invert that. 1 divided by the period will give me the frequency. Okay? So that was a lot. Let's go over that again. So we're going to divide by 20 to get to the period, the time it takes for 1 revolution. And then the frequency, the number of revolutions in 1 second, we're going to divide the period. Sorry, we're going to invert the period. It'll be 1 divided by my 3rd column here. So my 4th column is 1 over this column. A good idea is create these tables in Excel, and then you can use Excel to actually do those calculations for you. Since you're going to have to do, 6, 12, 18 different calculations, you can have it do it for you. Okay? So notice in this one, where we're changing our tension force, you're going to have to decide on a radius and a mass. Make sure you write them down somewhere, but we're going to keep them constant. We're not going to change them. We're going to keep the radius the same and M2, the spinning mass, the same. Make sure you write them down. Okay, that'll be our first procedure. Our second one is when we're going to change the radius, but we're going to keep the 2 masses the same. So you're going to choose 3 different radiuses, radii, I guess. Measure the period for 20, and again, calculate the frequency. Record the mass, the spinning mass and the hanging mass. Don't change them. And then do the same thing for varying the spinning mass. So we're going to change the spinning mass, measure 20 revolutions, calculate the period, calculate the frequency, and write down the M1 and R, the hanging mass and the spinning, and the radius. If you have the hanging mass, that means we can calculate the centripetal force, right? Anytime we have M1, remember that M1 is related to the centripetal force. Okay, so you can have all these tables, and then we're going to graph them. We're going to make 3 graphs first of all. Wait, what do you want for a lab? Okay, we'll get to the graphs in a second. What's my lab going to look like? All right, so first of all, step 1, title page. Okay, don't need a picture. Just put your title in the middle, on the right bottom. I'm going to add on the home page. Let's go to the website here. If you go to the home page of our website, go to the home page of our website and scroll down. There is, oh, maybe I didn't put it on here. Oh no. Okay, so I noticed that now. There's no lab expectation sheet. Okay, so I'm gonna attach a lab expectation sheet here. Sorry, I don't have that on the website yet. Good to know. Okay, so I'm gonna go over this quickly. All the details will be on the lab expectation sheet that will be on the website. All right, so title page, number one, put your name, date, course code, my name, bottom right corner. Then you can do an introduction. Now, this is going to be maybe new for you. The introduction is basically a one-page, double-spaced sort of background information. Let's say you were trying to explain this lab to a grade 11 physics student, and they don't know anything. So you're going to try to teach them quickly in your own words what's the point of the lab and what's the background information that you need. All right, it's a little bit tricky, and it's probably going to take a while for you guys to get the hang of this, but it's very important. It's just sort of, it frames the lab in a way that you're going to understand the point. Right? It forces you to think about, why are we doing the lab, and what are the things I need to know to do the lab. Imagine you're trying to teach somebody who doesn't know anything about circular motion. What are the big ideas, and what is the point? What are we trying to do? Like, for example, in this lab, we're trying to see what the relationship between centripetal force, mass, radius, and frequency are. We're trying to look for we're trying to look for that relationship. Okay, we're trying to find out, we're trying to derive an equation, basically. So as I increase the centripetal force, my mass will increase. If I increase the mass, my centripetal force will increase, or will it decrease? What are the proportionalities? How are they related? So that's the why of the lab. But you're also going to have to go into, like, if you use any terms like period or frequency, explain what that means. Okay, so don't be too wordy. It should be a full page. A regular font, doesn't matter. I don't care what font you use. Calibri 11 or Times New Roman 12 or something like that. Just double space it to make it easier for me to mark. Okay, so that'll be the first 2 pages right away. Title page, introduction. Then you're going to tell me a hypothesis. So how do you think they're related? And here, it doesn't have to be much. Just tell me, as the centripetal force increases, the frequency will increase or decrease. As the spinning mass increases, the frequency will. As the radius increases, the frequency will increase, decrease. Okay. So tell me what you think the relationships are, and it doesn't have to be exact. It's proportional to an inverse square. Just as one increases, does the other one increase or decrease? What do you think? All right, and why? Next, this might be new for you as well. Give me a quick little procedure. So what you do here is basically summarize what you're going to do in the lab, and we're going to use the past passive voice. So we did. Okay, we're talking about what you describe how you did the lab. Okay, in the past passive voice. If you need any more details on that, just check on our lab sheet. The one I'll post it on the team site, and I'll put it on the thing on our website. Okay. Next, what's after that? Observations. Okay, data tables. So that'll be the tables I just showed you. Okay, we're gonna put all those data tables in. Then you're going to make some graphs. Okay, you're gonna make 6 graphs altogether here. Okay, 6 graphs. So for your graphs, we're going to do first just frequency versus centripetal force, frequency versus radius, and frequency versus mass, so the spinning mass. Okay, so these will not be linear. Okay, then you're going to have to do 3 more where you make them linear, just like we did in our first assignment. Okay. And then we're going to try to compare what we got with what we would expect. I'm going to go over this a little bit more. And then a conclusion where you write, and sources of error. So let's go over this a little bit more in more detail. So the graphs. So the first 3 graphs you're going to do is going to be as I increase the centripetal force, what happens to my frequency? As I change my radius, what happens to my frequency? As I change my mass, what happens to my frequency? Make sure when you label your axes, you have your units there. Okay, so those will be the first three graphs. They won't be linear. I won't spoil what they'll look like, but you'll find out. Okay. Now, let's think about the equation. This is the equation in our notes. The centripetal force is equal to 4 pi squared, so this is just a number, it's a constant, multiplied by the mass times the radius times the frequency squared. So if I isolate for frequency, or if I get frequency by itself, and then I take the centripetal force out, I'm going to get this expression here, which is linear, right? My y is f squared. This is like y equals mx. My y is f squared. My x, my independent variable, is fc, the centripetal force. And my slope now is going to be this constant, right? Because we're not changing our mass or our radius. We defined those at the beginning of our experiment. So this will be a constant. It'll be a number. You can calculate it. So that will give us an expected value. This is what we would expect from the lab. So not from the lab, from theory, okay? So you can calculate 1 divided by 4 pi squared multiplied by the mass. In this case, this will be the spinning mass. So m2 times the radius. And then you can do the same thing for the radius graph. Right? If I isolate for f squared and I take the 1 over r out this time, now my dependent variable will be f squared, my independent variable will be 1 over r, and the slope of my graph will be the centripetal force, which we're not changing because we're not changing our number of washers, and we're not changing the spinning mass. We're only changing the radius. So the slope of my line will be this red term. And the same thing for my mass. I can take out 1 over m, and I have a new slope. So the centripetal force divided by 4 pi squared, again, just a constant, and again divided by the radius, whatever number that was. My head's in the way. Sorry. So that'll give you 3 graphs, right, with three known slopes. So these would be my expected values. Now, just a quick spoiler what the graphs are going to look like. These are the graphs, right, when they're made linear, right? We're going to have frequency squared measured in hertz squared. Notice whatever you do to the variable is what happens to the unit as well. Okay, and the centripetal force, we're not going to change that. Right? If we go back here, notice it was f squared equal to something constant times fc. And in the same way, we have frequency squared versus 1 over r. Another way you can express 1 over something is to the power of -1. So this will be radius minus 1, and measured again also in meters minus 1. And then you can do the same thing for our changing spinning mass, but it was 1 over m2, or m2 to the power of -1, measured in kilograms minus 1 versus frequency squared. And you're going to get lab values for these slopes, right? You're going to get slopes, and they should be equal to this, right? This is going to be my lab value. That is hideous. Excuse me. That's my lab value, and this is my expected value. Okay, and we want to show that these are the same or off by a certain amount. Okay, so this slope for this first graph, when we've linearized it, should be equal to that constant. And the second graph, it should be equal to these values. So those are our expected values. You're going to get a number, right? You're going to get 3 points, right? Because there was 3 different data points. Add a trend line using Excel, right? It'll give you the slope of it. And whatever that slope is, it'll tell you that number. So we'll have 2 different numbers. A number that we get from our lab, from our slope, and a number that we're going to get from theory, which we calculate. And we're going to compare them by checking what we call the percent error. So you're going to take your lab value, whatever that number was. This is going to be our slopes, right, for our graph. And the expected value, this is what you're going to calculate. That like 1 over 4 pi squared MR, let's say. I think that's what it was for the first one. That's a 4, not a 2. Okay, so that should be that'll be our expected value. So you take your lab value, subtract that from our expected value, absolute value of that. So if it's negative, just don't worry about it, ignore the negative, and divide it by the expected value, multiply by 100, and it'll tell you, my answer was, for example, I have no idea what your numbers are going to be, but it'll be like 7% off or something like that. And I'll tell you how close you are, how close you think you were in your data to get an answer. Okay? And once you have a percent error, then you can discuss where that error came from. And that's our last thing I want you to discuss, after conclusions, of course, is what were some things that caused error? Now, when we talk about errors in lab, we don't mean like, I made a mistake. I clicked the wrong button. I put something in the wrong place. That's not a source of error. Instead, sources of error are systematic. They're actually they're baked into the lab itself. They're things that we can't control, like a measurement error, for example. I can measure it as well as I can, but there's always going to be some sort of plus minus. Like if I use a ruler, typical rulers have millimeters, and that's our smallest division. So we say that is the in the case of that ruler, that's the error. It's plus or minus a millimeter, right? I can measure something as 13.2 centimeters, plus or minus 0.1 centimeters. Another thing we can talk about is approximations. What are some things that we didn't take into account? What are some things that we assumed? Is the path perfectly circular? This is a virtual lab, so there's probably not very many of those. And what are some unaccounted things like friction and that sort of stuff? Things that we didn't take into consideration. All right? Because this is virtual, it's mostly just going to be measurement errors. Okay? All right. So this has turned into a half-an-hour video. Did not expect that. Oh, wait. There's a lot of things. Okay? So is that it? Yeah. Let's go back to our... Here we go. So again, lab format. So title page, introduction, hypothesis. What do you think is going to happen? How do you think the variables are related? Procedure. Just a quick. You can use just use a paragraph, or if you want, you can use just bullet points there. I don't care, either one. But make sure it's in past passive voice. Observations are your data tables. You should have 3 in this case. Analysis is your graphs. So you'll have, and including here is slopes. Now, since this is all done and the slope calculations are all done in Excel, you don't have to write, slope is rise over run or something like that. You just say, put it on the graph itself, right? So that's part of this, is you make the graphs and include slopes. So I'm going to say including slopes. Then we're going to have our comparison using our percent errors. This is your percent error calculation. Then a conclusion, were you right or not? And then what are sources of error? And that's it. All right. So that's everything that you need to do for our Centripetal lab. All right. So any questions, feel free to ask me. Send in, an email or in Teams. And, best of luck. All right. I'll be talking to you later.